Hi! In the previous video, we have covered what are monotone sequences and the properties of convergent sequences. Now we shall introduce the idea of a subsequence. And so a subsequence is basically part of your main sequence, but you only choose the terms in the sequence in an increasing fashion. So it's hard to say, but let me just show you an example and then you'll understand. So for example, we have a sequence x1, x2, x3, x4, x5, and so on. Then we just choose the even terms. So x2, x4, x6, x8, and so on. Then this is known as a subsequence. So it's a sequence that arises from your original sequence. So for example, we have 1/2, 1/3 all the way. Then we just choose the even index term. So it's 1/2, 1/4, 1/6, and so on. And the limit of a subsequence will just be a subsequential limit. And so a subsequence is it's just a sequence, but now you just pick the terms from your original sequence. And so a lot of the properties and proving things for subsequence are the same as a regular sequence. So you don't need to be too confused about it. But now we just want to know how is a subsequence going to relate back to an original sequence. So if the original sequence converges, then of course any subsequence will converge. So the proof is quite simple. If you're just given any epsilon, then we can know that for there will exist an n such that xn minus x is less than epsilon. And because the subsequence are chosen in an increasing manner, at one point you have an index that exceeds n. And afterwards all these will also exceed n. But it may not be in like a step or one step. Like maybe it's xn and then the next subsequent term will be xn plus 5 from your main sequence. And so all these terms will now be larger than some value. And then for all these terms larger than k, x and k minus x will be less than epsilon. And so this subsequence will converge to x. And it's quite easy to do the converse, because if every subsequence converges to the same limit, then of course xn converge to x, because xn is a subsequence itself. So subsequence is really just a notation lah. And so let's just look at more properties of subsequences now. So we can say that this sequence is divergent, and the subsequence converges to 1. So you can have an original sequence being divergent, but the subsequence still being convergent. Although if, like in this proposition, if every subsequence converge, then you know that being an original sequence being a subsequence will also converge. But let's say maybe not all the subsequences here converge, then you can't say that the original sequence converge. And then we use this idea of a subsequence, and actually for every sequence now we can find a subsequence that is monotone. And this works for any ordered field. And the proof of it is a little interesting and very ingenious, and you have to make this idea of a peak. So basically a peak is a point where every other point is smaller than it. So in this case, this is a peak. These are all peaks. Every point after xm is a peak. For here, only the top points are the peak, because from here to here there is this point such that it is greater than all these points. So every point above it is a peak. Then here is a peak, here's a peak, here's a peak. So I hope you understand what is peak, but you can honestly read more online and play to understand it better, or you can rewatch this video again. And after you have considered what is a peak, then there are two types of graphs or two types of sequences. One where there's infinitely many peaks, and the negation of that will be finitely many. And so if you have infinitely many peaks, like in this case, then you can create a decreasing chain. And so this subsequence is a decreasing subsequence. And let's say that you have finitely many peaks. Then we can index these peaks in a way such that we now obtain an increasing subsequence using these peaks. So the way to index it is over here, as given in the textbook by Shelbert and Bertley. So I'll leave it to you to understand how the indexing works. But if you have infinitely, then you can see the graph that you can do it in a decreasing fashion. And if you have finitely many, then for example, let's say you have a peak over here. So to have finitely many is a bit hard to draw, but the idea is that now because you only have finitely many points that are greater than every other point, you can always pick an infinite number of elements that is below these peaks, and it will increase towards it, these peaks. So then you obtain a subsequence. And so with that, it comes that we have the monotone subsequence theorem. And so if you're just given a random sequence, you always have a subsequence that is monotone. And this comes to my last point, which makes use of the fact that with the monotone subsequence, we will have a subsequence that is monotone. And because in real numbers, we have a bounded sequence, it will be convergent. And so now, it says that a bounded sequence of real numbers will have a convergent subsequence. Because now, only in a real numbers will a bounded sequence be convergent, based on a proof that was given 2 videos back. So if you want to check it out again, you can rewatch the video. And because now we know that this sequence is bounded, the subsequence within it is bounded. And being monotone will mean that the subsequence will converge, because every bounded sequence, that every monotone sequence that is bounded converges in the real numbers. And so this subsequence is convergent. And so this is the Blazano-Weierstrass theorem, where a bounded sequence of real numbers has a convergent subsequence. So that's all for today's video. I hope you have enjoyed this bite-sized video and understand more about subsequence now. In the next video, we shall continue proving more and more techniques in real numbers. Thank you.